Hello, everybody. In today's presentation, we want to showcase some of the powers of Discovery simulation. It's a tool to clean up the geometry and prepare the geometry for CFD analysis or mechanical analysis. But Discovery in itself also has a solver which can be used to do basic CFD analysis and mechanical or electromagnetic analysis. So in today's video, we will look into how Discovery can be used to run a fluid flow simulation in a commercial swimming pool. Now, in this case, the commercial swimming pool is a setup where you have the traditional pool area, and then you also have this small section, which is typically called a lazy pool, lazy river. Actually, so the idea is that the liquid will be recirculating in the main region, and then there will be a certain stream of liquid which will form and move across in this region, preferably at a little higher speed, leading to the formation of a river system within the pool. And we will see how we can set up such a case in Discovery. So a little bit about the geometry. It's a pool geometry which is generated within Discovery, and I have already named the section, so you can see that the top surface has been named as the free surface. Then there are the walls, so your internal walls at this region, and the bottom part. Then you have one inlet stream over here, a second inlet stream which is named as large inlet in this region, and then you have three outlets at the bottom, 1, 2, and 3. So using these boundary conditions, what I want to do is I want to simulate the flow within this pool by varying the geometry of the pool and the flow rate from these inputs. I want to see how the fluid flow or the flow vectors are affected, how the flow direction changes within the pool. So first of all, we will move to our explore mode. In the explore mode, we will now click on the fluid flow simulation. We want to set up the inlet boundaries first. So under the advanced selection, we can always select the inlet small and set up the velocity for 0.25 meters per second and click OK. Similarly, we can also select inlet large. This is again our velocity of 0.25 meters per second. Click OK. Now we want to set up for the outlet. Here, 1, 2, and 3, and set it up as 0 Pascal. So we have the outlets set. What we want is I want to set up this top surface as a free slip condition so that this does not imply any flow resistance to the wall because of viscosity. So you can select the wall boundary condition and click free slip and click OK. All the other walls are automatically selected as a no slip wall boundary condition, as you can see over here. So with this, and the material is already selected to be water, but of course, the user has an option of changing material from this large material database that Discovery already has. So once you have set up this problem with the velocity inlet and pressure outlet boundary condition, you can actually now set up to see whether the analysis can be run or not. If the setup is not 100% complete, the system will tell you with a notification that, so in my case, it is flow outlet 11 found in the same surface as flow outlet 12 is applied. So let's delete this and Now we can simulate the run. As soon as I hit this calculate button, we will be able to see how the vectors look like. And so let's try that once more. So as soon as I hit the calculate button, we should be able to see how the calculation looks like. Let's change the velocity field so that we can visualize it better. Okay, so as you can see, I'm changing the flow at the inlet and the outlet and how the flow is kind of changing at different location. So if I change this to 1 meters per second, you will immediately see how the calculation changes and how the flow distribution is changing within the system. So as long as this hexagon has this halo which is moving around, that means the calculation is still computing. Once you do not see the halo anymore, that means the calculation is computed. Now, at this point, we are only using one inlet. What I can do is I can also assign another inlet. And we can now see the flow is being recomputed. Change the scales. And you can see just by adding a secondary inlet, how the flow in the system has been completely changed. And the calculation hardly takes a few seconds. Now what I can do is I can change this value to a lower value, and the flow will automatically update again. So you can see that how the design changes can be, how multiple design changes can be done in order to understand the flow behavior inside a, say, for example, commercial pool. What you can also do is you can click on this geometry and you can change the orientation of this geometry using the move tool. So say, for example, I have rotated this and now the flow will be computed again. And we can see how the final flow calculation will look like once the orientation has been updated in the geometry and the calculation has been completed. You can also use particles to kind of check how the flow will look like in a different manner. So you can change the speed. You can also change the size of the particles. And you can also use an injector such as this into a location to understand how does the flow at that local location looks like. So you can always refresh it. And again, place it into a location of interest. So let's say over here. This location, I reset it and see how the flow kind of looks like in this region. Of course, you will have to change the scales to actually see the correct color of velocity on these small injected particles. You can change this from velocity the static pressure. And you can also create section planes like this. These section planes can be moved different locations. See how the pressure at different locations is throughout the domain. Okay. Similarly, you can look at the velocities. And if you enable the contours on the flow region, you can select all the faces inside of all the bodies. And then you can create some volume rendering for the problem. And that will give you a more holistic understanding of how the flow profile looks like inside the system. Now, next, let's add gravity to the system, because at this point, gravity has not been added. So once we add gravity into the system, we will also be able to solve for natural circulation. So in this case, the fluid temperature is set to 22 degrees centigrade, and I have already added a convective heat transfer to the walls. So let's change the wall. And we have two different temperatures. And now we can also compute for temperature. So now what is happening is we have flow coming in at 1 meters per second at 30 degrees centigrade in the small inlet. And then we have flow coming in at 0.25 meters per second at 22 degrees centigrade at this large inlet. At the same time, the whole pool is losing heat to 10 degrees centigrade at a rate of 10 watt per meter square degree centigrade. So the convective heat transfer is set to 10 watt per meter square Kelvin, and the temperature is set to 10 degrees centigrade. So that is the ambient temperature. And when you try to look at the final solution of what the average pool temperature will be under such a condition, you can then look at the analysis. And based on this analysis, if we have this kind of setup and a certain degree of heat loss from the pool going out, we will have an average pool temperature close to approximately 22 degrees centigrade or 23 degrees centigrade. Now, let's change this a little bit. Let's switch this to 22 degrees centigrade and change this to 30 degrees centigrade and see how the pool temperature varies now. Now you can see that the overall pool temperature has increased to approximately 25 degrees centigrade. However, the calculation is still running because you can see the flow, and now it has completed. So this is how the flow calculation will look like, and the temperature distribution will look like once you have changed the inlet temperature. At the same time, you can also change the dimensions in this pool. So you can change this angle, you can change this angle to see how changing various dimension in the pool will affect the flow. So if I use the pull tool and pull this, make this thing a little bit larger, and we can immediately then see what the effect on the temperature distribution and the flow distribution will be like. So what we are seeing right now is the temperature distribution. And now on top of this, I can add the vectors to show how the flow distribution will look like. So the calculation is still computing, as we can see the halo. Once the simulation has computed, and we will take a look at the final solution. So now the simulation is computed, and we can see how the pool temperature distribution will look like. If you want to remove the contours and just look at the temperature distribution on flow vectors, you can look at it. look at temperature, velocity distribution. So of course, with velocity, you will have to change the coloring a little bit to understand how the distribution looks like. And then, of course, you can create section planes and see how the temperature looks at different regions if the section plane is varied, and you can also move it across any directions or rotate it as you wish. So using these simulations, you can see that how many different variation I could run through in a very short amount of time. And this is effectively the power of GPU-based analysis and the power of discovery simulation, which uh, allows you to go through multiple scenarios. Discovery simulations provide you a very good understanding of the flow physics that is going on. But if you want to run more detailed analysis, say, for example, species transport, reactions inside the system, sedimentation, etc., you will eventually have to move this model into Ansys Fluent or CFX to run these kind of multi-phase models. So now in this model, if you want to run parametric analysis, you can actually set up a parametric analysis. So in this case, let's set up a parametric analysis. So you can add this parameter over here. And once you add something as a parameter over here, they will appear in this location. So let's quickly add them as parameters. So we have 3 parameters. And you can see that you can create defined parameters using a generator, which is already embedded within Discovery. So of course, if you add so many parameters, you will come up with these many different variations. So for the sake of time, let's remove some of them. So that will lead to 8 defined variations. Let's create the variations. Create the definite variables. And we can run. Select update all. So it will go through all the 8 parameters and update the results. And at the end of that update, we will be able to go through each one of those results separately to understand which one of the parameters set is actually best suited for our analysis, or which one of these parameters is, which one of this design variation is best suited for our application. As the results come up, you will see the results are up to date in this section, and anything which is not solved, you don't see that green ring on the top. Of course, as soon as the results are available, you will also see this max velocity, pressure, and maximum temperature available in the data set. As soon as the design variation are changing over here, you will also see the current run design variation updated. So this is the last design variation which is running, DV8. Once that is complete, we will be able to go through each one of the final results and choose the best option. So once the results are ready, you can also look at the final parametric variation results in terms of graph, where you can change the input conditions. So in our case, we have changed the flow inlet velocities and the flow inlet temperatures. And so if I look at the inlet velocity, and then on the y-axis, if I place what is the maximum temperature because of that inlet velocity, so I can see that if my inlet velocity is set to 1, my maximum temperature is approximately 33 compared to when my inlet velocity is set to 1.5. My maximum temperature is down at 30 degrees centigrade. Okay, so also, of course, there is this one variable which is like the maximum temperature is also dependent on what is the inlet and temperature. So if you look at it now, you can see a more consistent variation. So as the inlet temperature is lower, the overall temperature and the maximum temperature is also lower. As the inlet temperature in inlet number 10 is increased to higher temperatures, uh, so you have a much higher temperature in this case. So it effectively tells us that the inlet temperature, flow inlet and temperature has a big impact on how the temperature in the, or what the total temperature or the maximum temperature inside the vessel will be like. So with this, I would like to conclude this presentation. If you're interested in such kind of simulation, do feel free to go to our website and feel free to contact us. Thank you very much.